The purpose of this lab is to expand on Lab 1 to model the charged tapes as equally distributed lines of charge, rather than as a singular point charge. We're going to use this new model of charge to find the electric force that one tape exerts on another. A preview of the results is that when modeling the tape into 10 sections that are equally distributed, the charge exerted by tape A on tape B is 2.69983 e to the negative coulombs. The gravitational and electric force are equal in magnitude, and they both have a magnitude of 2.06 e to the negative 3 newtons. The key concepts that we're going to use are going to be Coulomb's law / superposition. We're going to use Coulomb's law to find the electric force due to a segment of tape and find the force from that particular location. Next, we're going to use gravitational force due to Earth, which is F equals mg, and we're also going to use Newton's second law. The net force is going to be equal to 0 in this case. The two assumptions that we can make are that each U-tape has an equal charge and is evenly distributed along the length of the tape, and air resistance can be ignored in our calculations. Some values from Lab 1, we're going to be using the same observed separation distance, which is 0.025 meters, and we can see the floating tape in the top right from the lab protocol. When we hold tape A close to tape B, these two do repel each other. They're both either positive or both either negative. On the bottom right, we can see the original free body diagram from Lab 1, where we modeled tape A as a single point charge, and we can see that the force from tape A and the force from gravity are equal but opposite. On the left, we can see the updated free body diagram where we model the tape A into 10 equally distributed segments, and we can see that this charge is evenly distributed, and each segment of the tape exerts a force onto tape B. When we sum up the forces from each of these segments, we get a force in the positive y direction. These are the calculations from Lab 1, where we calculated the gravitational force on tape B using the mass of the tape and the acceleration due to gravity, which gives us the value of 2.06 times 10 to the negative 3 newtons. Here we have where we use the force due to gravity to calculate the charge on the tape when we were modeling the entire piece of tape as a single point charge. This gave us a value of 1.196 times 10 to the negative 8 coulomb. However, in this lab, since we are modeling the tape as 10 evenly distributed segments, we had to create a Glowscript model to calculate total electric field from each of these segments onto tape B. We did this by first creating a function for the electric field, which calculates the field at a certain segment of the charged particle. From there, we created a model for the line charge, where we can model each of the tapes as a line of 10 different segments. Then we were able to calculate the electric field onto tape B from each segment of the 10 from tape A. After finding the electric field of each of the segments, we were able to find the force onto tape A and sum them all together to find the net force. In this case, the x components of the force do cancel out as they all have an equal but opposite component, and this can be proven by the symmetry argument. After modeling the net force, the net electric force and net gravitational force, we're able to get a model looking like this, where the magnitude of electric force and gravitational force are equal but opposite. We can see the purple arrows representing the electric force from each of the 10 components, and these all sum up to make the white arrow, which represents the net electric force from the bottom tape. In conclusion, we can think about two questions. First, what if we modeled each of the tapes as a single point charge like in the previous lab? The value from when we model it as a single point charge is 1.196 e to the negative 8 coulombs, which I showed the calculation for before, and the value for the line charge is 2.699 times 10 to the negative 8 coulombs, which we found by trial and error in the Glowscript model to make the net electric force equal but opposite to the gravitational force. These values differ by 77.2%. These values are calculated through different methods. The first one is calculated solely as if all the charge is centered in the center of the tape, whereas from the line charge, we calculate the net force 10 evenly distributed segments, and we assume that the charge is evenly distributed over those 10 segments. So this is going to create different values. The one from the line charge is likely to be more accurate, as in the real world, charge is not centered at the center of the tape. It's going to be distributed all over the tape. So by applying superposition principles, we were able to more accurately calculate the charge of a single tape. Some same possible sources of error from Lab 1 from our distance value calculated. For example, we have the lack of precision in measuring the tape width, length, and separation distance, which can affect our calculated charge values, as well as the improper handling of tape, where if we touch the tape too much, we can transfer charges between our hands and the tape. In further experiments, we can model this with even more segments of charge, which is going to give us an even more accurate model and allow us to calculate a more accurate charge value.